Alright, the final piece of this chapter are the aberrations that we encounter in optical systems. We're going to see a couple of different things. We'll see spherical aberrations. Spherical aberrations will occur both in lenses and mirrors. And then we'll also see chromatic aberrations, which is an effect due to the refraction of light. And we'll only see that in lenses. So they'll, just because of the nature of the lenses, they'll show various imperfections. So we'll call these aberrations. For spherical lenses and mirrors, rays at the outer edge focus at different focal points. Right? So if I have light that comes in here, it's going to focus at a certain focal point. Right? But if I have light that comes in here, now this is light, I'm drawing them as different colors, but this would be light of the same color, and we'll talk about when they're different colors later. But here, if I have light come into the center of the lens, it focuses at a slightly different focal point. And this is called spherical aberration. We quantify this just by saying the difference in this F, we'll call this F1, and this F2. The amount of spherical aberration that you would have would be equal to F2 minus F1. Alright? This also occurs in mirrors quite a bit. So if I have light rays that come in here, they're going to focus at a particular focal point. And if I have light rays that come into the center of the mirror, they will focus at a slightly different focal point. Right, so this occurs in both the lenses and mirrors, and it's just due to the way the light rays focus at the outer edges. They will focus at different focal points. So due to the spherical nature of the lens or the mirror. You can correct this in a number of different ways. So you can correct spherical aberrations. In mirrors, you can, instead of using a spherical mirror, you can use a parabolic mirror. So this would be a parabolic mirror. And parabolic mirrors do not demonstrate this at all. So here, if I have light rays that come in to the outer part of the mirror, they will focus at a particular focal point. And then if I have light rays that come into the center part of the mirror, they focus at exactly the same focal point. So that's one way to get around it, is just by using a parabolic mirror. Now, in lenses, usually the way that you get around it is by putting an aperture. So you have these rays that come in, they focus somewhere, and then you have additional rays that come in like that. And usually what people do, you can actually create a system of optics with a number of different lenses that will correct for this. But usually the easier and cheaper way is to just put an aperture on the outer edge of the lens. And that just blocks all of this light. And it minimizes the effect of the spherical aberration. So those are two ways to get rid of it. For a mirror, you can use a parabolic mirror. And for a lens, you can use an aperture. It's the easiest way and the most common. Now there's another type of aberration. They're called chromatic aberrations. These only occur in lenses. They occur because the index of refraction is dependent upon the wavelength. We saw this in a previous chapter. Remember, this was the reason that prism spectrometers work. That if we plot, not lambda, but n versus lambda, it looks like this. Right? As the wavelength increases, the index decreases for most materials, for glass, for example. Then light of different colors, or wavelengths, that enter a lens at the same position will focus at a different focal point. And this aberration occurs only in lenses, as I said, because in mirrors, there's no refraction. So for example, let's see, we get red light coming in here. Let's see, red light has a smaller index of refraction, so it's not going to bend very much. So red light will focus out there. And then if we have blue light coming in to the same part of the lens, it will focus at a different part like this. Really, the only way to get rid of this is to use a system of lenses. I suppose you could do the similar thing as with the aperture by blocking certain colors of light using a filter. But the most common thing is use a system of lenses with diverging lenses as well, and that will correct for this, at least to a certain extent. I believe that is the end of the chapter here. In the next chapter, we'll deal with diffraction.